to cap off the chapter, I mean, we've dealt with Ampere's law throughout the chapter, and we've mostly dealt with this side because it's easy, and we've dealt with this side using symmetry. But I just want to show you a case where we don't have symmetry, and if we actually go and take the integral. Of course, we're going to stick to a fairly easy case, but just to quickly get that line integral fairly quickly. Now, just looking at this, we have a loop with some parallel magnetic field lines, and we can choose to go around the loop in any way. Let's choose to go this way so that our positive is out of the page. In any case, you see that it's enclosing no current. So, of course, you expect the line integral around the entire loop is 0. We know that already from Ampere's law. But, just as practice, I guess, they want us to get the line integral for each line and then add it up. Because each line has a different direction, let's name these 1, 2, 3, and 4. So for the first one, we have our dl in that direction. Our b always goes up in that direction, and we are always interested in this angle between them when you take the dot product, because b dl, we don't have the circle there because it's not a closed loop, it's just a line in space. We know this holds constant for the entire length, and let's name that length. Let's call this width and length, so that's width and length. So we know that we can take that cross product by taking the amplitude of each of the two vectors, multiplied by cosine of that angle. Simple dot product thing. But that angle, since we're not given this phi, we have to relate it to theta. Looks like that's theta, so it's actually 180 degrees minus theta. So let's clean this up a little bit. Of course, you can think of looking at the cosine graph and doing various transformation, but in this case, I probably prefer to do it using the difference of angles. So I have cosine, cosine, and cosine is always backwards. So if you have minus, you get a plus. You get 180 degrees, theta, 180 degrees, theta. What's cosine of 180? Cosine of 180 is -1. So negative cosine, and the sine of 180 is 0. Number 2, we have length L looking like that, and my B looks like this, where there's my theta. So again, we will do this integral being magnitude of B times magnitude of L, because for the whole side it's going to be the same. And again, we do cos phi, right? The angle between the two vectors. And in this case, that angle happens to be 90 plus theta. And again, I'll break this up into BL cos, cos minus sine, sine. We got 90 degrees, 9 theta, 9 degrees, and theta. Where we know that cosine of 90 is 0, and sine of 90 is 1. So we end up with BL sine theta. Let's circle these so we can keep track of it. For loop number 3, we have the entire length W. Our B is simply theta, so this is nice and quick. Oh hey, look, this is the exact opposite of that. Why would it not be? Because we're just going in the same magnetic field in the exact opposite direction. And when we do number 4, we have BL cosine. The angle in this case looks like this. We have L here, B there, and then the angle is this guy. So this is 90 minus theta, which this one I know is just simply going to be sine theta, because 90 minus theta, that's simply in a triangle. So this is theta, that's 90 minus theta. So sine and cosine will be flipped around. And that is the exact opposite as that. So we got each side, and then the total sum, of course, is them all added together, but you get a big fat 0. We could have, of course, made our lives a whole lot easier by taking a loop that's like that, so that we know we have b times L, 0, negative b times L, because they go in opposite direction, and 0, which also gets us a big fat 0. But the advantage of doing this, we have kind of shown that this is true in general. No matter what loop you take, it's going to give you 0 as given by Ampere's law. As long as you're enclosing no current, you will have that line integral evaluate to 0. For more complex shape, of course, this line integral is completely valid, so you could do a numerical integration thing to actually do it little bit by little bit at a time. And this is done as a simulation numerically for more complex geometry.